June, I went to Brighton, at Brighton Ruby, and but we didn't get to talk that, we met, but we didn't get to talk that much. And that's because she was always surrounded by other people, absorbed by the conversation. Even last week, I was at Uruko, and there were a few people that said, say hi to Elena for me. So let's give a warm welcome to Elena.
All right. Hi, everyone. I see the sound is working, so that's good. Yeah, thanks for joining me today. Second day. It's been really cool. I'm really impressed with the quality of the talks so far. I'm pretty sure I'm coming back next year, if Adrian is doing next year. I don't know if you've noticed, everyone keeps using the word friendly. I think we should do like a drinking game or something at this point, because it's like everywhere. But I think that's a good sign. Okay, so let me start my stuff here. Wrong screen. Yeah, let's do that. Nope. Nope. Other one. Yeah, that one. If I could see. See, I tried to look cool, so I don't have my glasses. All right, so I'm going to be talking to you about service modeling. My name's Elena. I work at GitHub. I should preface this by saying this is a project I've been working on for the last couple of months, and what I hope you get out of it is to get a peek under the hood at GitHub and hear my story for the last few months. I'm going to try avoiding the clicker because it seems to be a bit, it has a personality. Okay, so about me a little bit. You can find all my socials at that address. Flexing a bit, I can get my own link at GitHub. I also use the Pikachu emoji because that's my team's emoji, and we're quite attached to it. It's Detective Pikachu because we do investigations. I'm also Romanian. It's good to be at a Ruby conference in Romania. That feels good. It's very satisfying to see this put so well, so I'm very proud. I also studied nearby at University of Bucharest, computer science in 2006, which it's not that long ago, right? Now I live in London. And I've been working mostly in Rails for the last 14 years. I'm in the performance engineering team at GitHub for the last couple of months. And I enjoy terrible puns, so if you have terrible puns, tell them to me. I love it. And learning new things. Yeah. So before I start, I want to say a few words about Chris Nova. She's the reason my team was founded. She was our tech lead. You might know her from her work with eBPF, her book on cloud-native infrastructure, The Nova Show. She's the founder of Hachyderm and the Navinli Foundation for Open Source. Sadly, she passed away in a climbing accident last month at 36 years old. And I just want to commemorate her. She was a very kind, funny, passionate person, and we still deeply feel the loss of her on our team. And we partnered on this service modeling project. It was something close to her heart. She wanted to shine a light for developers to really see what kind of load they're putting on our resources and educate them on how to do better, how to write performant code. We'll miss you, Chris. Thank you. Right, so what is it? What is service modeling? Well, it's a standard process to find and document bottlenecks and performance opportunities at GitHub. That's the definition we have in the docs. We have docs. It's a collaborative process. We hope to work with the respective service owners together to fix problems. And it also leverages something we've created called a performance testing environment. I'm going to talk about that a little bit later. But why? Why do this? Well, GitHub is, I don't know if you know this, one of the largest Rails monoliths in the world. We know we want strongly isolated vertical slices of our application. We also want to know what the performance of a specific endpoint is at runtime with real traffic. And then we want to educate engineers about this so they develop an awareness of what their code is doing. So less YOLO, more precision. And while we have service separation and good observability, we're unable to say exactly for an endpoint what is the load on our resources. And when I say resources, I mean CPU consumption, memory, number of database connections, number of MySQL queries, cache hits and misses at that level. So this makes it hard to do capacity planning. And we have countless requests at the moment from teams asking us, okay, if I scale out this, what's the downstream effect? I need to know this, right? Yeah, and just to clarify, GitHub runs on Unicorn. So when you hear me say Unicorn, for example, we consume an entire Unicorn worker per request. When you hear me talking about Unicorn workers, you can interpret it as the number of requests we can process at the same time. Rails now actually ships with Puma by default, but this wasn't the case when GitHub was started. And we do have Puma in some places, but the main one is Unicorn. Yeah. Also, I want to clarify for everyone, if you don't know what N+1 queries are, just a quick overview. The definition is a performance problem in which the application makes multiple database queries instead of making a single query to return or modify the data. So in our case, this is a Rails example. Say you have books. An author has many books. The book belongs to author. In the first line, we say, well, third line, we fetch all of the books. That's cool. That's one query. But then if we want to fetch a resource on that, on any of the objects returned, we then fire off another n queries for each of them. And what we really want is one query that fetches everything, right? So when you hear me talking about N+1 queries, this is a performance problem that we're looking to find. Cool. Okay, so what did we do? We started by profiling one of the oldest services at GitHub, which is issues. There's tons of tech debt. There are dragons. It's lovely. I can tell you a lot of stories about it. But we start with this because it's also the place where we have the most experienced people in terms of performance optimizations. So we can work together and learn. So what have we found? I'm going to start with the end, and I'm going to tell you how we got here. Believe it or not, over 40% of all rows fetched by the monolith are one table. There be dragons. It's the permissions table. And it's because we make a lot of small queries to check that each piece of data that you're viewing, you're allowed to see it, right? We're very adamant that security is done properly, right? But you can see here that it's starting to show, right? Yeah. So that's one thing we didn't expect. Oh, one table. That means we can focus our attention to optimizing this and have an effect in the whole monolith, not just GitHub issues. So that's good news. What else? 50% of traffic at GitHub is served by 6 controllers. We didn't know that. Again, really good news. I mean, we can strategically optimize these controllers to speed up a large part of our requests. That's really good news. I should clarify, there's actually 2 parts here. I've simplified just to kind of show you the effect, but we actually have a front end and a REST API. And I'm showing you the front end here, but for the REST API, it's actually 4 controllers, so it's even better. Yeah. Yeah, so this is getting into more specifics. This is what happens when you create an issue. This is quite a long example, a long trace. It takes 3.56 seconds. And actually, we spend 0.9 seconds actually creating the issue. The rest of it is work that we could do in the background, updating related resources, right? Scheduling things, stuff that doesn't need to be making the user wait during the request, right? Yeah, this is a diagram of what happens when you create an issue. Like, try to keep this in your mind next time you go, new issue. This is what fires off. I did this by hand. I drank, I think, 2 coffees, not too much, but now we have an automated tool to do this, but at first we just wanted to see what it looks like, right? So this is all the MySQL queries that are fired. You can see we're calling to Aqueduct, we're doing background jobs. this is it. I couldn't fit it all on the slide. It's quite long. Yeah. Yeah, and finally, we found a future possible bottleneck. So for those of you that don't know, I don't know Nigeria if you're here. If you are, don't discount React. You might need it in the future. So GitHub's plan is to move to React, move our pages to React. And what that means, if you don't know, is in the old experience, we'd load the page once, right? All your resources have been fetched. You're done, right? We can measure that. That's cool. Now you load the first page. It's in React. It's server-side rendered. Cool. It might be actually faster than the old experience. But then what happens is you continue interacting with that page without reloading it, right? And that will fire GraphQL requests back to our databases. So it'll fetch more resources. And what we want to know is, okay, what is the total load now that you're putting on our backend when you're interacting with this page, right? So as more and more pages are moving to React, we need to stay one step ahead and be able to observe the effects. At the moment, there's not a lot, but like I said, we want to stay one step ahead. So what it really means is that the workload characterization, this is like a technical term, is changing. So we plan to invest more in resource isolation. Maybe some of you know that we have a public GraphQL API. I'm not talking about that one. This is a new one that's specifically designed to interact with React. Yeah, so that one isn't isolated. Yeah, so we want to control the blast radius. If this gets overwhelmed, we don't want it to take down the site. We don't want it to consume all of our unicorn workers that are available to process requests. Cool. Okay, so what does it look like? That's me after 2 coffees. These are the steps. I'm going to talk you through them. The first 2 are pretty straightforward. It gets interesting on the 3rd step, so I'm going to quickly go through them. So first, you need to gather request data. I should mention that when we started, we kind of needed to make some decisions about what to profile because GitHub Issues is a massive service. So we decided to narrow it down to the REST API because it actually takes more traffic than the front end. So we decided to go there. So first, we made a list of our request paths, and then we needed to understand which ones are receiving the most traffic. So we want to sort the requests by their load, and usually that's requests per second. And this allows us to prioritize high-impact areas. And like I said, then we need to make a decision. The REST API has over 180 endpoints. Imagine me doing 180 of those diagrams. I would probably die. So there's 3 criteria that you can use to prioritize. You can choose the endpoints that have the highest load, so receiving the most traffic, the ones that have the highest latency, or the ones that are the most important to the business, right? And for us, we chose to focus on the endpoints that map to CRUD operations. So create, read, update, delete, and the index page as a start. Yep, and like I said, only REST. Okay, yeah. Second one is actually drawing the diagram. Sometimes it's hard to find the code, believe it or not, in a beast monolith. It's hard. It's hard to understand all of the places that have effect. So it takes a while. You obtain a trace of the request, like I showed you. A flame graph. I'm going to show you a lovely flame graph. I'm excited about it. And then you kind of have to build your own awareness by poring over these and trying to connect the code to the tracing. And then you draw a diagram. Here's another one. This is list issues. This one's smaller. I still couldn't fit it on a slide, but it is smaller. Yeah, this is what happens. Yeah. Cool, so that gets interesting. You've mapped your requests. Now you want to understand the downstream effects. How do you do that? So you want to determine the dependencies for each of your endpoints. Databases, caches, calls to internal services, what's going on. So we used the use method by Brendan Gregg in his book. He defines this in the Systems Performance book. So what this does is it recommends you iterate through each of your dependencies and check these 3 markers. So utilization, saturation, errors. And this is recommended to be used early in an investigation to identify systemic bottlenecks, right? We actually had our own version, Nova's version, use P method, where P stands for procedural. Where does our code wait? Where is it waiting for work to be done that we could speed up? Okay, so armed with this new method, we take another look at our life cycle of our request. This is the process we go through. So like I said, identify resources, we choose one. We start with errors. We start with these because errors are usually quick and objective, so you can see what's going on quickly. Utilization comes afterwards. How much CPU memory is this particular endpoint putting on this particular database? How many rows is it fetching? How many tables is it using? And so on, and so on, and so on. And saturation is next. Any level of saturation can be an issue, right? This is like an example, how we mapped it. We've mapped it to dashboards and metrics that we care about. And then, like I said, there's also the procedural step. Where does the code wait? This is a flame graph for list issues. Maybe you can already tell something like an n+1 query smells somewhere down there on the right. It's really cool because you can just look at a flame graph and see, oh, there's some fragmentation happening here. Let me look into that. And that is actually an n+1 query, a massive one. So yeah, flame graphs are your friend. Okay, cool. So we've gathered all this data. Now we need to choose, like from all these metrics, what do you want to monitor? What do you think you want to demonstrate later that you've made an impact on? So average latency, how much time we spend making MySQL queries, things like that. And we need to make sure that the appropriate measurements are captured, so you might do some work to add instrumentation to emit these metrics. Yeah, and then we have another step that involves a new performance testing environment. We call it the Large Unicorn Collider. I didn't come up with the name. I think it's really cool. I'm actually quite jealous. But yeah, so what this does is it lets us measure compute utilization by running each of those endpoints through this environment. It can receive a small percentage of live traffic from github.com. And it receives the same deployments as the normal environment, so it's always up to date. And it helps us observe the real workload, the real load that we're putting on our systems. Yeah. Yeah, and finally, we want to create a dashboard. This is like the list of databases that Create Issues is using, and that's like a visualization of it. I can show you the dashboard as well. That one. There we go. This is scoped to create issues. This is all the metrics that we want to watch on it. Reads, writes. You can see how many reads and writes are happening at the moment. Memory allocation. There's also like an overall profiling in terms of CPU and metrics. Yeah, lots of other stuff. So you want to end up with something like this to track. Yeah. Okay. So you've drawn out the diagram, you've collected data, you have a good understanding of the code and what dependencies you have. Now you want to identify places where the code could be optimized. And this depends entirely on the data you've collected so far. There's no one way to recommend this, but I can give you some examples. So the things that we saw were, can we identify places where we can make unbounded SQL calls? Surprisingly, more than we wanted to. Yes. Are we doing things synchronously that could be in the background? Are we overfetching resources? Are we leveraging caching as much as we can? Are there n+1 queries? And does this code have tests? Because sometimes it doesn't, and that's really close to my heart, very important. Yeah. Cool. So at the end, we have a final report. We want to keep it short and sweet so that the team can just skim it. We don't want them to lose interest halfway. So 1 or 2 pages. We will identify 3 bottlenecks that we want them to know about and we can work together on. And then we communicate the conclusions. Okay, so how do we measure success? Like I said, we collaborate. We have a dashboard. We know where we're tracking now, so we can measure the impact of any of our changes. We celebrate. And then we do our best to share knowledge through blog posts and educational material and talks. Cool. So if you want to do something like this, this is the toolbox we've had, the USP method, tracing tool, flame graphs, diagramming, dashboards, and consider measuring real traffic. And that's it. Thank you.